Hi everyone, I'm Mo Chengguo.
Junjie
Pei Nan Zhao. We are fourth-year ECSE students. This year we've completed our final year project on designing a wireless physiological monitor.
In research field, continuous monitoring of vital signs are often required for animal experiments and patient study. The aim of our project design is to improve the flexibility and the efficiency of a physiological monitoring over a long period of time. The device is able to monitor ECG, blood oxygen level, and heart rate simultaneously with a battery life around 3 hours. The monitor signals are transmitted to user personal computer wirelessly through Bluetooth. We also developed a user interface to display the real-time signal and retrieve the previous monitor data. The device runs off a single 9-volt battery with a battery life of 3 to 4 hours with continuous monitoring. The device uses buck converter to convert 9V down to 3.3V, supplying power for Arduino, heart rate monitor, oximeter pulse sensor, and the Bluetooth module, and using linear regulator convert voltage to 5V for LCD module. In terms of microcontroller, we choose Arduino MKR Wi-Fi 1010 as a central processor for the device. It contains 8 digital I/O pins and 7 analog pins, providing enough I/O pins for the multifunctional circuit. It has a relatively low power consumption, portable size, and provides TCP/IP protocol, which makes it suitable for a battery-powered wearable device. The AD8232 board has been chosen to measure the electrical activity of the heart by connecting 3 electrodes RA, LA, RL to objects right arm, left arm, right leg, respectively, which is shown in the right image. Then the output signal will be transmitted to microcontroller by connecting to its analog pin. The MAX 30102 oximeter pulse sensor includes 2 LEDs, a photodetector, optimized optics, and a low-noise analog signal processing to detect pulse oximetry. One LED emits red light while the second LED emits infrared light. The device will monitor the absorption level for both light and transmit the data to the microcontroller through an I2C channel by the photodetector. The HC05 Bluetooth module provides a wireless communication between PC and Arduino through a Bluetooth serial port protocol by accessing the RX-TX serial communication pipeline. The wireless signal convert is 10 meters. Where the Bluetooth is connected to other Bluetooth devices, the red LED will blink every 2 seconds. Without any connection, the light blinks faster and continuously in a periodic manner. The LCD 1620 is a display module which is used to provide information through displaying letters, numbers, and characters. In this device, the LCD is used to display the value of BPM and SpO2 without any transmission delay. Hence, it provides a benchmark for the real-time operation of the information displayed on the PC.
In this section, I'll introduce the signal processing of the monitoring system, including the processing procedures of ECG signal, pulse oximetry signal, and data transmissions. The raw ECG signal collected from the sensor is contaminated by both high-frequency and low-frequency noises. Hence, the first step is to apply filters to obtain a cleaner signal that will be displayed in real time and retained for further analysis. The frequency analysis of the raw ECG signal is performed by using Fourier transform in MATLAB. According to the power spectrum, the noise signal has 2 major frequency ranges: the low-frequency baseline wander below 6 Hz and high-frequency interference at 24 Hz. Additional considerations were taken into account when choosing the type of filtering used for ECG signal. To satisfy the user requirement of minimized latency for the real-time display, With the limited computational power of a microcontroller, an infinite impulse response filter was chosen as it has high computational efficiency and it's easy to implement. An IIR bandpass filter with a default passband of 6 to 24 Hz is designed utilizing an open-source real-time digital processing library for Arduino. Moreover, noise of the ECG signal was observed to have varied frequency ranges when monitoring different subjects or using different types of batteries. Considering the requirement of obtaining a clean signal under various conditions, the frequency range of the bandpass filter is designed to be adjustable, where the users can change the filter frequency in the user interface. After filtering, the heart rate is calculated using R-peak detection. In the user interface, the users can set up two thresholds on the real-time ECG plots. When the ECG signal reaches the upper threshold, it will be marked as a possible R-peak, and the time of the peak is recorded. The QRS complex will be confirmed when the lower threshold has been reached after an R-peak. Whenever two QRS complex has occurred, the time interval between R-peaks is obtained in seconds. Finally, the heart rate in beats per minute will be calculated. The heart rate is updated whenever a QRS complex has been detected. Differing from the IIR filter used in ECG signal processing, an finite impulse response filter is used to process the light reflection signal from the oximetry sensor. The FIR filter have a slower computing speed but produce a more stable result. The major reason for different choices of filters is that ECG signal can be heavily influenced by skeletal muscle movements. Therefore, an efficient filter such as IIR is suitable for ECG signal as it has a quick response to handle the rapid changes due to motion artifacts. Oppositely, light reflections from the oximetry is relatively stable in frequency domain. Thus, FIR filter could be used as it has a more stable performance, which produce a cleaner filtered signal compared to IIR. Followed by the filtering, a differential function is applied to the light reflection signal to identify the maximum points of the waveform. As each wave in the light reflection signal corresponds to a positive blood flow caused by heart contraction, the heart rate is calculated using the time interval between two maximum points of the waveform. To determine the blood oxygen level, both infrared and red light reflections are taken into account. The main value of infrared and red light signals are calculated over every 5 sampling period. When the sixth sample is detected, a coefficient Z is calculated according to the main and instantaneous light reflections. Finally, blood oxygen level SpO2 is calculated using the Z coefficient according to the equations provided by the manufacturer of the pulse oximetry sensor. The data is transmitted between users' PC and Arduino through a standard Bluetooth protocol by accessing the serial communication pipeline. To synchronize the signals from different sensors and prevent data loss, the different signals are encoded into a data frame before transmission and decoded at the receiving end.
Moreover, the real-time ECG plot will be displayed on the researcher's personal device with a delay of less than 5 seconds. The real-time plot and warning message allow the researchers to analyze data for any abnormalities. The data is transferred and stored in the PC for the future offline analysis with zero dropout rate.
So this is the user interface that has been produced with C# and SQL database backend. An initial version was presented to the researcher and feedback was taken into account during the interface development. The interface provides user with warnings for any wrong inputs and 3 modes, which are the ECG display mode, which display the ECG waveform and also the BPM values. You can change the mode by enter different number in the mode box. The second mode displaying the SpO2 waveform along with the SpO2 values and SpO2 BPM. In order to reduce the latency, The third mode will only display the numerical data we obtained from the previous mode. Finally, the data is sorted by different subjects, where the user can enter each subject's profile into the database through SQL and viewing the different recorded number and recorded values.
This is an example setup of the monitoring device during animal experiments. 3 ECG electrodes are clipped on animal according to 3-lead arrangement. The oximeter is clipped on an area with thin skin, such as outer ear. During animal surgery, the researchers will be able to keep track of the vital signals of the experimental animal using the LCD display. We had an opportunity of using our system to monitor the ECG of a rodent in a living animal experiment. While the monitored ECG signal is clean and the calculated heart rate is accurate, the ECG waveform of the monitored rodent was incomplete. It is because that the mouse has 5 times faster heart rate compared to human. While the system is able to plot the ECG of the human, the sampling rate of the device is not high enough to plot the full waveform of the rodent. The sampling rate of the device can be further increased by reducing the latency of the program or utilizing a microcontroller with faster computing speed. What's your point of view of wireless physiological monitoring?
Right. Yeah. Okay. So in the recordings and the work that we do here, we're dealing with very, very low signals, low voltage signals, and so they're highly susceptible to environmental noise, and wired systems carry noise. This is really annoying. It means that we have to shield every cable and be very careful with our grounding setup, and it takes a lot of time and energy. And so wireless monitoring systems like this just remove entire systems that could be carrying noise from the setup. It makes things easier, it makes them higher quality. So yeah, generally it's vastly preferable.
Yeah. What's your opinion in our FYP monitoring system as a researcher?
So it's interesting. It's really, really good start. Like, this has got everything that I want out of an ECG monitoring system, and then a little bit more. Perhaps still some tinkering to do though. I know that we had some trouble getting the rat heart rate and things like that. So there's a few kinks in the system, but what is presented here is essentially everything that we want out of an ECG system, right? So all the boxes are ticked.
Yeah. So just in your point of view, what could be the future developments of this monitoring device?
So where I go with this is really, I want to take another look at the software.
Yeah.
So I think that the biggest problems that we had using this was the data transfer rate to the computer, the computer filtering the signal correctly and then accurately and consistently detecting what the heartbeat was. The data itself looked fine, and the hardware seems really, really good. And so that's where I'd start. But it's really promising.
Yeah. Thanks for the feedbacks and comments you give to our FYP. Yeah, we might develop it in the future as a side project outside of our study.
Yeah.
Instead of using a box, a smaller and well-designed 3D printed container could be utilized to save space and improve the appearance of the devices. The second important improvement would be the transmitting and receiving rate in the user interface. In the current situation, a built-in read line function was used in receiving the data via Bluetooth. However, if the application could not handle the incoming data, the exist information would be stored in the read buffer, which lead to the delay. A better data separation structure would be designed based on the read exist built-in functions. Moreover, instead of storing all data in the same local device, a real-time cloud storage might be developed to help with the user to access data within different personal devices. This could be achieved by creating an IoT connected devices. Lastly, the power consumption of device could be considered to be minimized by implementing energy-friendly components and the standby modes for LCD display and other components.